This can help an athlete perform better overall. This data could be used to figure out how to optimize airtime, find the optimal angle for maximum distance, as well as help an athlete find the optimal speed one should go to get the maximum jump height and length without putting oneself in danger. You could extrapolate on this data based on the forces which allow for these different outcomes. The projectile skier initially moves at an increasing velocity or acceleration from the rest to the peak of the jump, where the y position increases upward. Then, the skier begins to decelerate and move downwards in the y direction. Overall, the skier moves forward in the x direction. During the beginning of the jump, the skier accelerates positively, while in the later part of the jump, after the peak, the skier begins to accelerate negatively. The acceleration of the whole motion averages out to be negative, as the fall after the jump is greater than the startup, which means that there is more time after the peak than before it. Therefore, there is a greater portion in which the skier slows down. We can conclude that the skier moves in an arc. The length of the arc is determined by several factors, one of which is the skier's acceleration. The skier's acceleration is made up in the beginning launch, when the skier is still on the ground. The skier starts to slow once the applied force from the skier pushing off the ground stops. This occurs the instant the skier is airborne.
For the position time graph of the horizontal motion, the skier moves positively in the x direction, which is red, and moves down in the y position, which is blue, because the skier is on a slight slope. For the velocity time graph of the horizontal motion, we could see that when moving horizontally, the skier moves at a nearly constant velocity, therefore there is a minimal acceleration. The quantities of motion we found for our horizontal launch were the position of 0.45 meters, the time of approximately 1 second, the initial velocity of 5.2 meters per second, the final velocity of 6.1 meters per second, the acceleration of 0.9 meters per second squared, and the mass of 84 kilograms. The horizontal launch free body diagram has a normal force and a gravitational force canceling out each other, and an applied force forward with no frictional force because of assuming no friction. The horizontal's launch of net force is equal to mass times acceleration, which is 84 times 0.9, which results in 75.6 newtons forward. Fnet is equal to Fa plus Fk, and kinetic friction is equal to 0. So therefore, the net force is equal to the applied force, which is again equal to 75.6 newtons forward. For the vertical motion, we found that a normal vertical jump on while skiing down a hill was far too similar to the projectile at an angle to the horizontal, so instead we used a skier jumping in place. The position time graph of the vertical motion sees the y position increase over time as the boots of the skier begin to jump. The x position is not important in this graph because he does not move left or right. The velocity time graph of the vertical motion sees the velocity increase as the skier's boots start to go off the ground until a final point where he begins to fall. The boots on the startup are first at rest and then accelerate until they leave the ground. The quantities of the vertical launch are a position of 0.3 meters, a time of 0.84 seconds, an initial velocity of 0 meters per second, a final velocity of 0.65 meters per second, and an acceleration of 0.77 meters per second squared, with a mass of 84 kilograms. The free body diagram of this vertical motion sees normal force and gravitational force equal out each other, with an applied force going up since he is jumping, with no frictional force since we are assuming no friction. The net force on the vertical launch object is equal to mass times acceleration, which is 84 kilograms times 0.65 meters per second squared, which gives a total of 54.6 newtons forward. We assume that net force is equal to applied force plus frictional force, but we know that frictional force is 0 because we are assuming that there is none. Therefore, the applied force is equal to the net force, which is again equal to 54.6 newtons forward. The position time graph for the projectile launch has the beginning of this motion as the skier clearly begins moving quickly in the y direction as well as in the x direction. Due to this change in position, it could be assumed that the velocity will increase at this point. The velocity time graph of the projectile launch sees the projectile startup clearly show a positive acceleration. The acceleration increases because there is a limited or no friction, which means the net force is greater than 0, and therefore it does accelerate. The quantities of motion for the projectile motion object is 1.62 meters, a time of 0.78 seconds, an initial velocity of 0, a final velocity of 2.69 meters per second, an acceleration of 3.433 meters per second squared, and a mass of 84 kilograms. The free body diagram of the projectile motions object sees normal force and gravitational force cancel out each other, with an applied force going at an angle upwards with no frictional force due to it being ignored. The net force for the projectile motion object is mass times acceleration, which ends up being 84 times 3.433, which gives us a total of 288.37 newtons forward. The applied force, we could assume, is equal to F net due to the fact that frictional force is 0, giving us an applied force of, again, 288.37 newtons.